Good afternoon, everyone. It is now afternoon here in Canada, at least where I am. Maybe parts of other Canada it's not. But I want to wish you all a very happy World Water Day. It's extremely important that we have to be talking about this so precious resource on this day. So my question is, what's moving your water? And on our screen right now, we see 4 of our FloNergia 4-inch pumps operating in an aquaculture facility here, not very far from our office here in Burlington, Ontario. My name is Paul Subject. I'm the CEO of FloNergia, and I wanted to just take a moment and just talk a little bit about the FloNergia story. FloNergia is a startup. We were incorporated in 2016. We developed our technology in collaboration with the University of Guelph, our airlift pump. And for those of you who know something about airlift pumps, they've been around for about 100 years. And we took that old design and we used computational fluid dynamics to develop an entirely new technology. And I have some here around me in the background. You can see them, and we'll talk a little bit more in detail about those at the end of my presentation. Our innovative patent pending technology is currently being sold around the world in aquaculture, agriculture, wastewater, and related markets around the world. And we are building a global network for our pumps. And currently we have distributors in Canada, the United States, and India. And we have distributor talks underway right now in Australia and Germany. So enough about us. Let's talk about the challenges with water companies. So what are the big challenges for UK water companies? Well, you know, it's expensive to move water. And energy is a big expense in the water business. And for example, you know, the UK water industries consume a huge percent of the electricity that the UK produces. The other problems are that pumps are expensive. They wear out. It's difficult to maintain them. And of course, as we know, the life cycle of rotating pump systems are many times the purchase price of those pumps. So they're very expensive. And the other issue is aeration generally is inefficient and it's expensive. It costs money, it costs energy to operate. So how do we solve those problems with our technology? Well, it's quite simple. Our technology uses only the water required for aeration alone to both pump and aerate water. We don't need to do both. This reduced energy profile, as you can imagine, if you only use one energy source, results in savings of 50 to 70% versus conventional aeration and centrifugal pumping systems combined. Our FloMove pumps have no moving parts. There's nothing inside them. We just use air and the design of the pump itself to actually move water. And our airlift pump technology has exceptional aeration properties versus conventional systems, up to 40% improved aeration efficiency versus paddle wheels and surface sprays. So you're probably wondering, okay, how does that work? How does our pump work? How does this old 100-year-old technology actually function? Well, so we'll talk a little bit about a conventional traditional system. In a traditional system, you need power for pumping water and you need power for aeration. Now for FloNergia, we get all of the power to move the water and aerate the water from that single blower. We don't need additional pumping. We can move water and aerate it at the same time. So what does that mean? Well, that results in 50 to 70% energy savings and substantially higher aeration efficiency versus conventional methods. So where do we go in a water treatment process? And this is kind of a standard kind of graphic I have here that I use that's part of the Canadian water treatment process of a typical water plant. And for FloNergia, we can be used in the pre-treatment and clarification system. We can be used in disinfection. We can be used in transfer of materials from one location to another. So let's talk about that in a little greater detail. So where would you use our pump in a pre-treatment section? So we can improve flocculation by aiding aeration. As we talked about, our aeration costs are substantially better than conventional systems, and we get pumping at the same time. We can help with chlorine or whatever your disinfectant is, your injection, because our technology can use intermittent injection as part of the airstream that we use to drive the pump. Additionally, we can transfer pumping in pumping applications, moving our water from one location to another. And the other unique part of our technology that's very interesting is that we can use it to pump and transfer sludge from one location to another. So a couple more benefits I wanted to talk about, spend a bit of time. So we can easily move heavy fluids and solid waste, and we've done that in various wastewater applications around the world. We have no moving parts. It can't be clogged. Our pumps are fabricated from food-grade plastic. There's nothing to corrode. There's no metal materials inside the pumps. Our pumps also facilitate carbon dioxide removal, which is a great feature for what we do in the aquaculture and agriculture marketplace, but it's also an interesting feature in other applications. Our pumps also disrupt thermal stratification, which in some applications is important, in other applications is less important. It depends on settling and temperature variations from surface to the bottom of a tank. We also improve DO substantially, and I have terrific numbers around that. And we range in our maximum size in terms of pumping is 710 US gallons per minute. Now you may say, oh, I have a requirement where I need thousands of gallons per minute. Well, we just group our pumps together to get the same volume output.
1 minute to Paul.
Thank you very much. So where are we around the world? We selected application. We have a 40,000 gallon tank with 3,600 gallons per minute in Canada. In Chile, we have an 80,000 gallon tank, 9,600 gallons per minute. In India, we have a transfer of a heavy sludge, 10,000 gallons, 120 gallons per minute. How do we plan to then enter the market? Through product trials and direct sales with key water companies, through technology licensing, but primarily through partnerships with engineers, consultants, and distributors. We would like to partner with appropriate companies to find water company sites for initial product demonstrations, work with engineers and consultants for easy integration into existing infrastructure, and develop our water industry distribution matrix in the UK market. Thank you for your time and attention. I'd love to answer any questions you have at this time.
Thank you, Paul. Again, another one brought in perfectly on time. So well done. Fantastic. Could you just pop your slides down so I can see the judges?
There we go.
Great. I'm going to be a bit, well, before I can see them, I'm just going to ask John, possibly, whether he might just like to start off.
Yeah, sure. Yeah, my head's just spinning a little bit, if I'm honest, like a pump, almost. So, yeah, I'm just trying to mark my mind here that we use, as well as centrifugal pumps, we basically cavity pumps, ram pumps, and the interchangeability of those with an airflow pump, which I've not come across before. I'm not an engineering background, so I think ultimately the number of this is going to be the business case. So it's the cost of capex, the Totex model, which is built up of obviously capex and then cost to operate. So you mentioned there the cost savings in operation. What's the difference in capex between an airflow pump and a standard model progressive cavity pump?
A great question, John. A super great question. So let's do it on a gallon per minute basis, US gallons per minute. So typically, and for example, this pump that's right behind me right here, that's our 8-inch pump. That 8-inch pump would sell for our manufacturer suggested retail price in the UK would be about £14.57. So if you think about what a standard 800 gallon per minute pump would put out, that gives you a pretty good benchmark.
So there's the capital cost, and then you'll be aware that we've got a public interest commitment. I think it's the first time I mentioned it today, remiss of us, to be net zero carbon emitters by 2030. I think we're pushing it to the back of our minds somewhat, but absolutely not, by the way. So I think it would be really helpful, as well as if there's an energy saving here, then that could be expressed in a carbon saving over standard solutions. So two assets become one asset, there's going to be a cost saving. But what does that mean in terms of carbon?
Well, that's a great question, and actually, I have data that I can share with you. I didn't prepare that for today, but we've spent a lot of time with the Canadian government because, of course, carbon footprint is a huge political question everywhere around the world, especially in Canada, as we produce a lot of materials that emit carbon. But I have data on that I'd happily share. But I think the thing that's really important to remember is that the electrical energy that you would take to run a centrifugal pump or any other rotating mechanism is completely displaced because we use the same energy that you would use to aerate your system. That very same blower runs our pump. So you don't need the duplication of both an aeration device and a rotating device. And that's where the energy savings comes in. But I'd be happy, John, to share with you the carbon footprint numbers that we've developed. They're very impressive.
That's great. And of course, as I'm just finishing up, I've got loads more questions put in my head. Things
Please
like
go ahead.
Mixing systems in sludge. There you go, Jonathan Abra brought in sludge again. Yes, sludge mixing systems, for example, activated sludge use. Can we cut out diffuser blocking and keeping things more mobile, for example, so we don't get sludge settling out? Far too much to talk about just now, but it's got me thinking. So that's great, Paul. Thank you.
Thank you, John.
Damien, I wonder whether, I know this is treatment technology. I've not been directing questions to you that are not directly in the environment regulators pitch, but I would imagine there's probably something here that might ring a bell.
Thank you, Alistair, and thank you, Paul. Great presentation. I was just wondering whether you have applied your technology and tested it in flood situations.
We have not. We have mostly stayed in the aquaculture, agriculture, wastewater marketplaces. We haven't tried it anyplace else yet. But because of the way the technology works, and remember I talked about the fact that it has no moving parts. It has no moving parts inside it. It won't clog. So if we can get air into it, we can pump. And just another little story that might give you a further illustration on how we can pump. This pump was originally developed to pump bitumen, which is a combination of basically dirt and very thixotropic petroleum products, and it did it with aplomb. So I think anything where there's debris, mud, debris, I want to say silt, etc., our pump can move it.
Great, thank you.
That's very interesting. Caroline, what do you think from your point of view? Your hand is raised as well, which is great.
Yeah, really interesting presentation. And I'm going to hold my hand up now and say this isn't an area of my expertise. So these are more comments than questions, although you may be able to add some additional insight to them. My questions were around linking back to what John said around that net zero carbon agenda. I'd written that down and noted that under the business case points, and thought that was a really strong area, but the need for more figures and evidence to support that. And then around the replacement rate of the various pumps within the systems, and being able to maybe better identify or support the water companies in identifying which pumps need replacing when, because they're not highly unlikely, unless it's the most amazing business case, to replace all of the pumps come what may. So the ability to provide better insight into that. And also then the question, again, really sorry for this is a naive question, but the connections between the different pumps, and whether, I always think about a footprint of a technology and whether it fits in the system. Have you put thought, I'm sure you have, into whether they would fit into the systems that we use within the UK and the different sizes of the connections? Apologies for my naivety there, but it was just a point to raise, and if you have any insight, then that's great.
Great questions and great points. So all of our pumps connect both internally or externally into existing systems. So we can pump from outside a tank or inside the tank, depending on how the pumps are located currently. How we actually link to the pump, it's quite simple. The pump itself, just let me grab this one. So this is a 6-inch pump, right? So flexible couplings top and bottom, basically. we can also design the coupling based on the existing system that's actually operating. So if we need threaded connections, we can do that. It doesn't really matter. This is a fabricated plastic part, so we can sub into just about any system there. So the substitution part is quite simple for us. To your other point, Carolyn, which was a great one, we'd love to work with a water company so that we could actually eke out all of the little opportunities for us to install our technology as older technology reaches its product life cycle. And that could be in injection, that could be in disinfection, that could be in pumping, that could be in sludge pumping. We'd like to be able to trial with a number of partners in order to establish those protocols. We've done it in wastewater in other countries, just not in the UK yet. I hope that answers your questions.
Yes, thank you very much.
Terrific. Matt Lewis, you've got your hand raised.
I love it that you said this is a 6-inch pump. It looks like a pipe to me.
It is a pipe.
We've got plenty of pipes.
Yeah.
Kind of what I was interested in is the operational maintenance require if I put some of these in. So is this something that my existing ops maintainers would be able to look after, or is this a new skill set that I'm going to require?
This pump, basically, as long as it gets air going to it, it operates. It doesn't collect biomaterials or anything like that, so it clogs the ports that are inside. So inside the pump here, there's micro holes. You can probably see them better on this particular version. There's some micro holes in there, and those micro holes are what create the aeration. You can just see them there in my camera. So they create the aeration, but air is coming out, water is not going in. So there's no issue about fouling, right? The other thing is that as long as the air that goes into the pump, so there's 2 ports that go into the pump here and here. The direction of flow is that direction, of course, the direction of the arrow. And we can regulate the amount of micro bubbles that are created and the amount of macro lift that we get by valving the air stream that goes into the pump. So of course you can't have more than 100% air. And for a typical blower that would put out, this particular pump runs a blower that'll put out about, I want to say about 150 CFM per cubic feet per minute. That's a typical aeration blower that you would find in an aeration application. So we can valve between these 2 ports and actually improve aeration or improve pumping. And so, of course, by operating the valves, we can manage the flow. But there's nothing new to learn here. It's basically a pump. If you have a good readout system with pump pressures and all those kinds of things on both sides of the pump, you can tell when the pump's operating.
Okay, and it would work in the same way as our current telemetry and etc. works on our pump.
Yes, sir. Yes, sir. Yes, absolutely, absolutely. And to your point, Matt, actually, we're working on. We have a sensor array that we've built that actually watches and reads it's a non-contact sensor array that manages the behavior of the pump. We're going to commercialize that later this year, and it operates basically with whatever kind of whatever interface technology you currently use. It operates basically using a smartphone.
Fab. So I need a compressor and a smartphone and I'm started.
You need a blower, not a compressor. Compressor is very expensive, Matt.
Matt Foster.
Yeah. Hi, Paul. Apologies if this is a simplistic question. Is there a distribution network application to this pump? Obviously, we've talked about lots of locations where air in water is good. In the distribution system, air in water is not so good. So I'm just wondering whether or not there is any application in the wider network as opposed to perhaps some of the treatment type applications that we've spoken about.
You know, an excellent question, Matt. We've never really talked about that yet, and we believe there's opportunities throughout the distribution network of how water is distributed. We'd really like to spend some time talking to some really smart engineering folks about where those opportunities lie.
Okay, so that's a maybe then, is it?
I mean, I would like it to be a firm yes, but I just honestly I don't know.
Okay, interesting.
Superb. We're just about there. Steve Quamby, you've got anything you'd like that to add? Yeah.
Poor Steve.
He's plagued all the way, isn't he?
You've fascinating, innovative pump, and I can't even work a computer laptop screen. Paul, in terms of basic physics, obviously the prime mover is still the air blower. What physical principle are you using for your motive power? Is it the Venturi principle? Is it a Pareto principle? Just for my benefit.
So we call it an annulus. You probably can't see it there, but there is a bit of a low pressure area that's created inside the pump where, and because of the buoyancy of air, there's the annulus right there. Because of the buoyancy of air and water, that's how we actually create movement, right? So because we create, basically it's called slug flow. We get a great big slug of air in here and it lifts the water up with it. And so we combine that with the aeration. So we get both aeration and slug flow at the same time, and that's what moves it. But you're right, there is a Venturi inside here, Steve, which creates just a very small low pressure region that moves water.
Yeah. So what lift can you get from that? Bearing in mind that you're using blowers, what magnification of lift you get? And one last question: do you get harmonic oscillations in that process because of the blowers?
We don't, because generally we don't encourage hard coupling. Flexible lines is fine. Then we don't get any of the harmonics. But generally, because we've mounted the tank the pump either in the tank or outside of the tank, the deadening effect of the attachment to the tank actually kills any harmonics that we see. But you're right that one of the things we also counsel against is super hard piping from the blower to the pump itself. And then you asked the second question. I'm sorry, I was busy thinking about the answer to the first before I got to that.
Yeah, we'll have to wrap up.
So you use a dead weight of. Okay.
I think we should wrap up if you don't mind, because we're just slightly overrun on there. Thank you ever so much, Paul. That was really, really interesting, and
thank you.
Lots to think about there, definitely.